can buy and sell. For a control center, you can buy and sell power. And so we have a sequential decision. And the market is a price for buying and selling. Assuming buying and selling are different, so we're buying and selling. Okay. And then we have all the intelligence from the smart grid. So that's the information from the smart grid sensor network. Okay. To summarize that mathematically, all that information is represented by a capital Y. Okay. So all that information coming in, and what does it give us? It gives us the knowledge of the stochastic component, the deterministic component and the stochastic component. So for the stochastic component, that gives us the idea, the probability distribution of the renewable generation, the probability distribution of the demand. So assuming at the end we have all these probability distribution, okay, not only the point estimate, not just a point, probability distribution. So if we have all of that. Now, this probability distribution gets better and better when we're getting closer to real-time operation. And this is, today we all know, just for point estimate, for the wind forecast, typically day-ahead wind forecast is not very useful. The error could be as big as 30%. This is a chart I took from Iberdrola. They say they can reach 16%, but that's probably the best they could do. But most of the wind forecast, the error is probably pretty large. The error is the wind forecast. Okay. But as you get closer and closer, a few hours ahead, okay, 3 or 4 hours ahead, then the error becomes reasonable. Okay. And if you look at a few minutes ahead, the error is pretty small. So some of the wind forecasts, they actually use the persistent forecast methodology. Just use this minute, the same as the next minute, is probably better than any of the time series, any of the artificial intelligence forecasting methodologies. So this is the idea. Okay, what I'm trying to say is our uncertainty decreases as we get closer to the operation. Okay, this is important. So we want to make sure supply and demand balance at the operating point. This is what it matters. At the end, we want to have balance. Okay, so every effort in dispatch will be made to balance supply and demand. Okay, but after all efforts are made, okay, we have to consider, okay, in the stochastic world, there's always a risk not meeting the supply and demand in the stochastic world. And that's the risk. Okay? And the risk of not having enough supply, the easiest way to measure the risk is the loss of load. And perhaps there's risk of too much supply. That may not be good as well. Greater than what you can immediately curtail, that's not good. That also contributes to imbalance. So you have the risk of not needing too much supply. These are the simplest risk measures. Okay, that's the simplest risk measures we can think of. We can develop more sophisticated measures of risk like what they do in the financial discipline. Okay, they do risk management all the time, so there are a number of risk measurements. Okay, so other measures are possible. So what we want to do is at the end, okay, at the last minute, when we do the forecast and so on, we want to make sure that probability is small. I want to point out, this is the probability distribution at the end, okay? At the very last end. That's the probability distribution. We want that risk to be small, to be acceptable. Small meaning acceptable. So what we have is a sequential decision process. Day ahead, hour ahead, load following, frequency, regulation. Okay. At each step, we decide on the deterministic controllable dispatch. So that's the dispatch decision we want to make. And the information coming in from the smart grid give us the probability distribution of the stochastic components. And we select the dispatch decisions to minimize the total cost, subject to the condition at the end, the risk of supply-demand imbalance is acceptable. So that's the idea of risk limiting at the very end. And the total cost consists of the day ahead cost, hour ahead adjustment cost. We do the adjustment. And load following adjustment cost. And frequency regulation adjustment cost. In other words, this formulation is different from the traditional one-shot optimal power flow type of decision or unit commitment type of decision. We look at all the adjustment into consideration. So this is the probabilistic formulation. Okay, so this is the formulation. The formulation looks very complex, very difficult. And if you give this to a graduate student, strange enough, they come up with beautiful results. Okay, this is what happened to Ram. He is now an assistant professor at Stanford University. Okay, he came out saying, "Yeah, okay, I take we have this problem, stochastic control problem, okay? And the solution is surprisingly simple. Okay? The solution is at each stage, okay, all you have to do is to determine two thresholds, okay, phi minus and phi plus. Okay? And if the current dispatch is below phi minus, you add. Above phi plus, you sell. Okay? You buy, you sell. Okay? So that becomes a very simple solution. Of course, these fees are not that easy to obtain. Okay? They are the solution of equation, and this is the form of the equation. Okay? This is the form of the equation. Has the probability distributions into that. It's rather complex. However, if all the probability distributions are Gaussian, okay, and there are only two numbers to characterize the probability distributions, and then the solution takes a simpler form. I don't mean the solution simple, okay? The form is simple. Okay? So it looks like the mu is the plus and minus something, okay? And in form, okay, okay, it looks like our traditional decision. Okay? You have the target value, and you have reserve, and the reserve has a lower reserve limit, upper reserve limit. So in terms of operation, it becomes similar to our traditional way of doing that. except the computation will be complex, assuming the computer can crank out all these numbers. Okay? And these thresholds can be computed either offline or updated online. Okay, I'm not going to go into the mathematics on the way to compute that. Okay, but let me just summarize the idea we propose for the risk limiting dispatch is we want to guarantee supply-demand balance at the time of operation. Okay, and within the risk level specified by the user. Okay, what is the risk level that's acceptable to you? Okay, this is like in the financial world. Okay, the banks are now required to put in enough cash, so that they don't have the risk of bankruptcy. Of course, that level is very important. Okay, before 2008, that level wasn't good enough, so we had the financial crisis. Now they strengthened that. But that's the idea of risk. And we have a sequential decision process, and the process based on the idea we separate the controllable dispatch to meet the stochastic generation and load, okay, the stochastic component. And we use the information provided by the sensor networks, and that information is provided, update at all the decision point, okay, updated. And the decision from the very beginning, we take into account the future adjustment, future possible adjustment, future possible scenarios, future possible, because of probability distributions, future possible distributions and their adjustment actions, all of them take into account. So it's holistic, taking into account. Those flexibility are taken into account. Okay. And the formulation is very general, can accommodate different market structures and different probability distributions in theory. And this is the core of a balanced cluster from the dispatch side. Okay? And this will be the major part of that. Okay, with that you say, well, because of the stochastic, so at the very end, there may still be fluctuations. Okay, those fluctuations in the imbalance that we cannot take care of. Okay? We won't be able to handle that at the end, the fluctuations. How do we do that? Well, we say we have exhausted our power in the supply side. So we have to focus on the demand side. What can we do on the demand side? So we want to design, people are talking about, design smart load to follow generation by demand response. Okay. We want to make it, really follow, okay, in the literal sense. And the idea of follow is like idea of a spring. Okay. The spring really follows things, right? Here's the spring. And if you have too much force, it pushes down, and the spring will bounce back. And if you pull it up, the spring will pull it back down. So this is the idea of a spring. Now, if we can make our load acting like a spring, would that be nice? Yeah, if we have a load that when the voltage is too high, the load will automatically bring the voltage down. when the voltage is low, the load will push the voltage back. Would that be nice? And if the supply power is low, and the voltage will somehow push it up, so the power consumption would still be constant, just like the spring. Too high, you know, it will make sure it pushes down. So this is the idea of spring. So if we can make an electric spring as a load, that will solve our problem, right? You know, so this is the idea of electric spring. We want to design. This. Okay. Of course, you know, mathematics. You know, if you have a difficult problem you give it to a graduate student to solve, when you come to a real thing, a graduate student probably will not be able to solve that. So, but if you give it to a competent colleague, that problem can also be solved. So here's my colleague from University of Hong Kong, Ron Wei. We discussed this, and then, you know, after a while, we came up with before that, I have to say another thing. Okay, before I say, you know, how do we realize that? Okay, so this is the idea. Okay, of the electric spring into the load. Okay. Now, we want to do that. We have to look at our load. Okay. Our load. Okay. Right now, we treat our load the same. Okay. Because we only look at the generation to follow the load. So the load is the king. Okay. We just follow the load, whatever that is. Okay. So we said, well, not all loads are created equal. Okay. Not all loads are created equal. Okay. Actually, there are some loads we care more. Okay. There are some loads we don't care. Okay. There are some loads we don't care. We can use direct load control, okay, because we don't care about it. Rather than the traditional thing, we don't care about that. We just cut it. Okay. We throw it away. We say, well, let's don't throw it away. We separate the load into two types. Okay. Those we care, those we don't care. Those are critical, some are non-critical. So we want to make sure the critical load has high quality, has, you know, acceptable quality, voltage quality, power consumption quality. These are typical load. Okay. And a part of the load, non-critical, we can play with that. Okay, so that's another idea we want to inject in. Okay, and then how do we do that? So first of all, we split the critical load and non-critical load. Okay. And non-critical load we can control that, so we put a control device into that. Okay. So what we want to make sure is, voltage here is what we want, power here is what we want, and here we don't care. Here we don't care, so we play with that, and we put a device here, and this device we call electric spring. We put this electric spring to do that. And this is the device Ron Wei has built in the lab. Okay. So this is the one he built. Okay. And then we want to do simulation. Being a device person, my colleague, Professor Hui, doesn't believe in computer simulation. Okay. I have some computer simulation, he doesn't believe that. He wants to have actual experimental test. Okay. So he went to Imperial College. He has a joint appointment with Imperial College. went to their lab to actually test this. So this is the system that we test. Put this his device in, and the load, the critical load, non-critical load, and here is the lab setup. There's the wind generator, physical wind generator, and then the grid power supply and the transmission line model. So this is the system, and this is the test result. And this is without electric spring on the left, and this is with the electric spring on the right, and this is the voltage, and this is the power. And this one is the critical load, and the non-critical load. Non-critical load is the, I believe, is the blue one. So let me summarize. I'm loading it over. Let me summarize. The world is moving towards drastic carbon reduction and renewable deployment, with Europe and California taking the lead. With the economic condition in Europe is declining, California is probably will take the lead. And large penetration of renewable requires paradigm shift in power system operation. Paradigm shift doesn't mean throw away the good things. So I still want to keep the good things. And people say, we want to move from generation following the load to load following generation, or from centralized to decentralized. We propose, not ideologically to do the traditional thing. We want to do what is probably, pragmatic. So we propose a smart grid with intelligent periphery, in which control intelligence is pushed down to the periphery, and to have a layer architecture so that they can coordinate to have a global balance. And in the grid architecture, the basic component is the cluster. And the cluster, we want to make sure the dispatch, we want to dispatch the controllable generation to follow the stochastic load and demand. And we have a sequential decision process to do that. And it's a holistic approach. And then to match the small variation, fluctuation, we propose, actually my colleagues have designed a smart load, the concept of electric spring to follow the fluctuation renewable generation. Of course, this is the basic concept. There are still a lot needs to be complete in order to complete this. But that's how the traditional power system evolves. Okay, the control center idea, started with the load balance, and then evolved into low frequency control, and then evolved into optimal power flow. So it's a step by step, but the basic concept we want to introduce here today. That completes my presentation today. Sorry, I'm taking 4 more minutes here on the water. Thank you very much. Thank you for your attention.
我们有请台湾电力公司系统规划处庄中良处长引言。
谢谢刚才吴教授的精彩演讲，非常难出的一个很高兴。因为刚才吴教授带了一个 smart load 的概念 ，electric grid， 专门来对抗这个renewable energy， 现在在调度上面的东西，这个可以让更安全的电网继续维持。那刚才这个吴教授也提到了这个smart grid with intelligent periphery 里面的有一个部分就是 self-healing capabilities， 就是接下来我们第二场这个刘教授、吴振清教授的这个演讲的内容。刘教授大家都很熟悉，也经常回到台湾跟大家来互动跟指导。刘教授的最新情况跟大家介绍一下。刘教授现在是在美国华盛顿大学任教。同时也是在爱尔兰的都柏林大学教授，所以两边跑啊。那他是这个华盛顿大学的Washington Energy Assistant Innovation Center 的主任。我想今天接下来他也谈到一些怎么样把这个台大刘志文教授现在正在研究 PMU 的这个技术呢发扬光大，用来做稳定的控制。会谈到两个部分。一个是比如说这个电力的误动作怎么样把它减少，第二个部分就是无脑运转怎么样把它控制。我想因为时间关系，我们接下来是不是大家热烈欢迎洪教授。
谢谢张处长的这个引言。Professor Liu from Taiwan University, we have a few Lius, so I know Professor Liu and Professor Wu, Professor Tomsovic, 各位先进distinguished guests. It's always a humbling experience for me to come back to Taiwan University because. I remember when I was a student here, we walked by the hallway, and there's a window there, and the professor published a paper, 2-page papers in I2 section. And so it made it into the window, and we all know, everybody knows that. When we walk by, we all admire the paper. And now today, Professor Liu is elected to I2 fellow. You know, it's a very highly competitive process. And that's a recognition of the accomplishment. But more importantly, I think when you look at the whole university, not just Taiwan University, but other universities as well, it's really a different home that we're coming back to. So I want to recognize the hard work and amazing, impressive progress. So, and today, I want to talk about self-healing, but before that, I should mention a few words about smart grid activities in the U.S. The U.S. government invested about $5 billion in the smart grid program. It's primarily pilot projects and demonstration projects. And with industry matching, it will be another $5 billion. So total maybe about $10 billion investment. And that program is ongoing, so it's probably, I say, 3 years plus in the process. And so, what kind of projects are ongoing? I think on the transmission side, a lot of work is about installing PMUs, the phasor measurement units, which Professor Liu is working on here, colleagues and power company as well. So PMU is installing PMU devices is a big component of the smart grid project. And one of the important issues in there is what do we do with the data? And I think using the data, with PMU, how do we actually use the data is still a very global R&D problem. There are some tools around, but I don't think it's very widely adopted, and I don't think it's very comprehensive yet. So that's one part. The other part is the smart grid in the distribution level. And in the distribution level, it's the smart meter, installing smart meters, and also the distribution distribution, automation, and renewable energy components. And that's the other part of the smart grid activities. And where I am right now, Washington State University in Pullman, it's one of the so-called smart cities, which means every customer in Pullman has already installed a smart meter. And Pullman is a very small town. If you have 5 cars, you see 5 cars on the street, that must be a traffic jam. However, it's a smart city, so everybody is a smart meter, and we are now in the process trying to figure out what will get the customers engaged. And that is an important question, because a local power company started a new program. What they do is this. They started the coupons of the program. If you join that program, they pay you $100 a year, and you allow the power company to control the temperature setting at your home by 2 degrees. What they told me is not too many people sign up. Not too many people. So that's very interesting. So in the distribution level, the big question is how do you engage the customer? What do the customer want? And that is a societal context. People don't necessarily react to money. Some people react to green, reduction of the carbon and global change. And some people react to competitiveness. For example, one thing I heard is they did another program. 2 high schools competing who is more energy efficient. And that smart meter project became highly successful. And that has nothing to do with it. So it's the competitive nature. But are we going to compete with our neighbors? I don't know. And so what we do, so this Energy System Innovation Center, that's listed here, I should recognize that. The purpose is to bring the societal context into smart grid technologies. So we have colleagues from sociology and psychology and the social science aspect bringing and blend with the power engineering. And we are trying to answer those type of questions. How to get customers engaged. If you don't get customer engaged, then the smart meter is just a computer meter. It doesn't do a lot more than that. So this is what I want to start with. Then the next thing I want to say is self-healing. Self-healing, this term has been around for more than 10 years. And I read self-healing in government documents. Self-healing term now appear in the popular magazines. So it has become a big popular term. And exactly how much, and it's been there for a while. So question is, what have we accomplished? And what can actually be done today? And so what I'm talking about today is perhaps a little bit narrow and technical, but if we talk about smart self-healing, then we have to include a few things. One is the monitoring capability, which is PMU-related work. That's one. 2 is the protection and control. And we start with what is already here for a long time, which is the Special Protection Scheme, SBS. That's a very basic form of defense system. And then you go to the defense system, reconfiguration, etc. And that will be the next thing. And then the last resort is the power system restoration. And power system restoration has been there for a long time too. So although I'm talking about some fairly specific technical topic, I would like you to keep in mind that when we talk about self-healing, we should include all that in our mind. So let me start with PMU. So what I want to do is this. I want to start with the PMU monitoring. So I want to talk about 3 things. One is I start with PMU monitoring, which a lot of people are doing. And we are doing some computational methods, and I want to share with you that part. The second question is, how do I use that PMU monitoring into a defense action reconfiguration? That's number 2. And then the third one is self-healing actions. What what kind of self-healing actions can I take if the system is heading to instability? So I hope the three things will tie together as the PMU applications. So PMU, and I should mention that in my hometown now, Pullman, it's also the home of SEL, the Schweitzer Engineering Laboratory. So we have a lot of PMUs in Pullman. And so cascading events, I don't need to say too much about this, but cascading events is going to happen again. It has happened. It has happened in Taiwan, and it has happened in US, Europe, and it's still happening. And I think statistically, if you look at the blackout statistics, then every 11 years there will be a major power outage, 11 years. And so we are all counting. So let me start with the PMU. So what can you do with the PMU? So if you look at the technical method of PMU application, maybe the existing method you can find in the industry is monitoring or damping coefficient. Damping. So they take PMU data. My colleague Manny Subrahmani, Washington State University, he has developed this software which has been installed in a few control centers, and it's about monitoring damping coefficients of the system. That's one. And what we are doing here, what I'm doing here is a little bit different methods. And this is, we are trying to look at the stability. We are trying to look at the waveform stability. That's the main idea here, waveform. And so this term, bear with me here, this diagonal exponent, this MLE, this is the index that we're trying to develop as a way to look at the waveform stability of the system. And what does waveform stability mean? I don't think I need this. So I'm going to apply the waveform stability to the power system swing behavior. So I'm using that's why we call rotor angle stability, because we have the machine models, and we all know the transient stability problem, and that's where we start. So with the transient stability problem, I collect the PMUs, and the PMUs will give me the voltage, the angles and voltage, and so angle is a very important part of that. And so we should be able to look at the angles and try to say something about system dynamics. That's the basic. Okay. And so why don't I a little bit. Maybe a little bit jumping, but I will come back. So what is the difference? So what we are doing and with PMU here. So if you look at this picture, this is the dynamics of the system, right? So think of it as the voltage angles. So the power system is swinging here. And so what we're trying to do is to see if you perturb the trajectory. If the trajectory is going to be perturbed by whatever change in the system. The initial condition has a perturbation. If you perturb the initial condition of the power system, will the waveform stay fairly stable as before, or is it going to fly? That is the simple question that we're trying to answer with the PMUs. And it makes sense because with the PMUs, we give me waveforms, and I want to say something about system stability. And so I will ask the question, what does the waveform look like in the future? And which means if there's a perturbation, is it going to stay fairly stable, or is it going to go? That's the question we're trying to answer. And if you compare this concept, it's a little bit different from what we have been doing in as nonlinear system stability, because there we are more used to taking the dynamic model, find the equilibrium points, find the stability of the equilibrium points, and then you draw a conclusion about stability regions, etc. And So this is a little bit different concept. But with the PMU, the nature of the data we are getting, it seems to be fairly natural to look at this. So this the optimal exponent, what we can get is this. We can compute the optimal exponent, which is MLE, and this will provide a bound for me. You can see if the initial condition has been perturbed, has been changed, then how about the follow-on trajectory? If you have from this, it's fairly simple. If you see if this is a negative number, then this will die down eventually, which means it will remain stable, trending. And if you have a positive number, MLE is a positive number here, then you know exponential of a positive number is going to grow, which means I cannot guarantee the system. The waveform is going to stay as before. Okay, so that's the basic idea of what we're trying to do. And how can we do that? But to do that, first I need the model. And that's why I showed you power system equations before, and I don't think I need to repeat them. So one of my former students at Iowa State, he did some work to analyze the optimal exponent, and then he showed us, he did some work about how we can use the optimal exponent to show the asymptotic stability, etc. His name is J-A-N, Y-A-N, and he's now a Midwest ISO. So we have a couple of things to answer before we can actually use that technology. So I have 3 questions. One, all right, the PMUs will give me the data, but it's going to come with a window, because I take the data and I have to choose the window size, and then I have to be able to draw some conclusion from that window. So, but then the next question is, how do I determine that window size? One question, right? Second question is observability. In the US, if you look at the eastern part or western interconnection, there are tens of thousands of buses and substations. And how many PMUs do we have right now? More than 1,000. And so you can see we are still very far from having complete observable network. But on the other hand, if you go across China, all 500 heavy substations have PMUs. So they are all completely observable with PMUs. And so it's very different, but in the US, observability is still a very major problem. So, which means I have to have a way to take the available measurements, PMUs, and compute or estimate the rest of it, which is unknown. So I need to have the optimization, the numerical methods to try to find that unmonitored portion of the network. And that's called observability traditionally, because observability implies that you can determine the whole system state based on what you can see from the outputs of the system. And then my third question is I need to be able to calculate the MLE online. Is there a fast method to calculate the optimal exponent? So the first question is the window. And so window is a little bit tricky because the power system can react in different ways. Sometimes it's slow, sometimes it's fast. And so it depends on what's happening, depends on what kind of dynamics you trigger. It will give you different behavior. So our first answer is fine. I will do a good number of simulations for different kinds of scenarios. And then I will look at the waveforms of the system dynamics. And then I do a spectral analysis, find all the frequencies in that waveforms. And then I will look at the range of the frequencies of these waveforms. And then I look at the low end of a frequency. For example, if the low end of a frequency is say 0.5 hertz, then I will 0.5 hertz means you get a cycle every 2 seconds. Then I will set my window to 2 seconds. And that way I can capture at least one cycle of the frequencies that's part of that dynamic waveform. So that's how we try to answer this question. But we are still not very happy with this answer. So this is still something we are working. That's the first question. Second question is about unmonitored portion. So I have power system that's unmonitored. Buses without PMUs and some with PMUs. And you can see, if I tell you there are 50,000 buses in the eastern part of the US, and we have 1,000 PMUs, so approximately, roughly, very roughly, then you can see, no matter where you put it, it's very hard to claim that I can observe the whole system with that very partially or minimally observed system. And so we have to have a way to continue improving that as we increase the PMU. But the way we are doing that to compute the unmonitored portion is you do a small step dynamic integration of your dynamic equation. So this doesn't matter what it is. You take the dynamic equation and then you integrate a very small step. And the small step means you convert it into algebraic equations. And some of that is monitored, so it's known. Some of it's unmonitored, it becomes unknown. And so if you use this implicit integration method, then you're actually solving a set of nonlinear equations. Somewhat related to the power flow equation, but of course it's not, because it improves the dynamic equation, and you do take a small step integration. Now you have to solve this set of equations, nonlinear equations, and that will give you the unmonitored portion. Is it always solvable? That's a question related to observability. And I think the quick answer is if you choose the right, well, obviously for the nonlinear equation, you are going to need the Jacobian and Newton methods and all that kind of thing. So if you can assure your Jacobian is non-singular, then you'll be okay. Right? And how do you assure your Jacobian is non-singular? You can always do that. Taking a small step. That's a very short and quick answer. Okay. Make sure your steps are small enough that you will not run into problems in memory. All right, so let me let me show you an example. So we took the 200 bus system, which has the characteristics of the western part of the U.S. And now what are we going to do? What we are going to do is set the window to 5 seconds. And the 5 seconds is, as I said, based on how we, based on the way I mentioned earlier. We compute the unmonitored system. And then we have also numerical methods to calculate the outbound exponent. And so now I have a new index for the system. And how well does it work? So this is just the calibration of the model, so I will skip that. I'll show you how that, here is the reactant exponent. So this is the traditional way. So we take a list of contingencies, and that will be the generators, lines, etc. And as I said, the simple criteria is if your exponent is negative, then it will be asymptotically stable, and if it's positive, it will be unstable. So this is how that judgment is done. And then the question is, how about window size? So if I change the window size, how is it going to affect my results? So you can see here for this, if you look at MLE 3-second window, 4-second window, 5-second window, to 10-second window. Right? So you increase the window. You know, obviously, if I have a very wide window, then a lot of things could happen in between. So you may not be able to get a good feel of what is the most important. If you have a very small window, then you might only get a partial view of what's the big thing that's happening. So exactly what is the right side is a very important question. So you can see here for narrow window, it's turning from negative number to positive number. But then afterward, it seems to stay as a positive number. And then if you look at other cases, there's a similar case here. But you can see this, the upper exponent is changing as you increase the window size. That's expected. And that also tells you are looking, you are getting a different feel of how system is changing. So we are now testing that PMU algorithm with everything. So we are now developing computational